Last time we were talking about the mean value theorem, and this is a mean value theorem example that we hadn't finished. So let me finish up this example in the next one, and then we'll move on to local extrema. So, as I mentioned last time, mean value theorem, our real use of the mean value theorem is to do integrals in chapter 4. So you'll see a lot of artificial problems here in section 3.2, and the only point of the problem is to use mean value theorem. So this is one such problem. So the problem says, suppose f of x is differentiable and that f prime of x is greater than or equal to 2 for x between 0 and 5. And we're also told that f of 1 equals 10. And we're asked to find a lower bound for f of 4. So first of all, let's make sure we get what they mean by lower bound. So here we're trying to, a lower bound for f of 4. Here I'm looking at the range and I'm trying to say, what's the lowest possible value for the range? That's what, for the y value of f of 4, not the entire range. For f of 4, what's the lowest possible y value? So it seems like a random problem, and it is. And I mean, let me show you. Let's look at the information they gave us. So here's an x-axis, and we're told, I specifically want to, look at this piece of information here, that f prime of x is greater than or equal to 2 for x between 0 and 5. So let me mark 0 and 5. So maybe 0 is right there, 5 is right here, and let me write that down. So here's 0, and here's 5. So I think one thing that we should notice, and this is certainly not a coincidence, is that they tell us information about f of 1, and they're asking about what's happening at f of 4. And so it's not by coincidence that you'll notice 1 and 4 are in between 0 and 5. And so 1 and 4, we're in this region where the derivative is greater than or equal to 2. And we're given information about the derivative, right? We're told f prime is greater than or equal to 2, but we want to find information about the original function f of 4. And so the only thing we have right now that really connects up the original function and the derivative is the mean value theorem. And here, because they tell us the function is differentiable, we know that differentiability implies continuity. So here, they've set up the stage for us to use a mean value theorem, in that they told us it's differentiable, they've given us information about the derivative, they want us to find something about the function, and the main connection with the derivative and information about the function would be, certainly one connection would be the mean value theorem. And so again here, we use the fact that it's differentiable. Remember that if it's differentiable on 0 to 5, then it'll be differentiable on 1 to 4, and differentiability implies continuity. So we get the continuity and differentiability from this statement here about the derivative being greater than or equal to 2 from 0 to 5. So now that I know it's continuous and differentiable, we can use the mean value theorem. The mean value theorem says if the function is continuous on the closed interval and differentiable on the open interval, then there exists at least one number c in the open interval such that f prime of c equals f of b minus f of a over b minus a. Here a and b are 1 and 4. And so we have f of c equals f of 4 minus f of 1 over 4 minus 1. And f of 1, they gave us information about f of 1. So I can plug that in. And now the mean value theorem, the whole reason we used it is because now we have a bridge between the function. So look here, we have f of 4 minus f of 1 over 4 minus 1 equals f prime of c. But we also know f prime is going to be greater than or equal to 2. So here these two, we can connect up these two ideas now. So f of 4 minus 10 over 3, which is equal to f prime of c. But since c is between 0 and 5, we know f prime of c will be greater than or equal to 2. So in this case, we can eliminate the middleman right here. So here we can conclude that f of 4 minus 10 divided by 3 is greater than or equal to 2, because it's equal to something that's greater than or equal to 2. And now we're basically home free, because now we just want to solve for f of 4, because ultimately we wanted to make a statement about f of 4. So I'm going to move 3 to the other side and multiply by 2 and move the 10 over. The negative 10 will become positive. So if f of 4 is greater than 10 plus 3 times 2, or a lower bound for f of 4 would be 16. So we'd say, you know, the value of the function at 4 does not get below 16, is at the lowest 16. And so I believe there's a homework problem like this. It is quite random, and it is completely set up so that you can solve this with mean value theorem. You know, like I said, the book is really trying to find, you know, problems that they can assign to the students on mean value theorem without actually, you know, using it for the actual use. You know, the book hasn't started discussing integration theory and doesn't want to get that technical yet. So you kind of find these artificial problems. All right, this next problem, there's a problem like this in the homework. It's a very math major type of problem in that it requires that we solve this problem using logic. Okay, so I wanted to do an example. This is, you know, it's an okay problem for homework. It's definitely not the type of problem I would put on a test. It's a little too theoretical, a little too mathy, you know, a little too math majory. So here, remember, this is a tricky problem. And if we read the question, it says, prove that the polynomial f of x equal to 1 plus 2x plus x cubed plus 4x to the 5th does not have 2 or more distinct real roots. So remember, a root is just the same as an x-intercept. And just a little background, it's been proven that an nth degree polynomial will have n roots. So here this n, the roots could be complex or real. So here, this 5th degree polynomial should have, in theory, 5 roots. And what the problem is asking us to prove is that of those 5 roots, it does not have 2 or more that are real numbers, i.e., you know, that the other roots are all distinct, complex. So here, when we say real, we mean like real number as opposed to complex. Okay, like I said, this is a kind of a tricky problem, and it's a very standard problem that a math major might see, you know, like maybe a little further on, not even in Calc 1 necessarily, but anyway, there is a problem like this in the homework, so I wanted to do one for you. So this problem uses logic to solve it. So we don't do just a bunch of math steps and churn out an answer. You know, at the beginning, that's how math goes. But the further you go along in your math career, you'll see that we'll start to use more techniques that are less direct, more techniques that involve logic and other sorts of strategies. So in particular, this problem uses a strategy called proof by contradiction. So math majors will study different proof strategies in a class called discrete math, which I also teach. And proof by contradiction is one of them. So if you haven't seen proof by contradiction, this might be your first time, and this might be your introduction to it. Proof by contradiction is very counterintuitive, and that's why it's a little tricky. So let me give you a very silly example of proof by contradiction. So suppose I want to prove fire is hot, okay? And I'm going to do it using proof by contradiction. So the technique of proof by contradiction, the way the logic is, we assume the opposite of what we're trying to prove. And then based on that opposite assumption, we get a contradiction with reality. And so then we go back and say, oh, the opposite of what I was trying to prove is actually false. So the opposite of the opposite must be true, and the opposite of the opposite is what we started out with. So let me do a very stupid example. Suppose I want to prove fire is hot using proof by contradiction. First, I'm going to assume that fire is cold, because that's how contradiction works. That's the technique. Assume fire is cold. And then I run an experiment, like I stick my hand in the fire. When I stick my hand in the fire, what happens to my hand, people? What happens to my hand when I stick my hand in the fire, people? Anyone? Anyone?
Gets burnt.
It burns. It burns. So then I say, well, I guess my assumption that fire is cold must have been wrong. And in fact, the opposite of fire is cold must be true, i.e. fire is hot. Please don't try this at home. I mean, I'm sure we all tried this, right? When we were a little kid, at some point we touched something that we didn't know was hot and then learned that it was hot, a light bulb or something. So, all right, folks, proof by contradiction is counterintuitive. Let me do that. Now let me apply proof by contradiction to this situation. And since proof by contradiction is so sneaky and tricky, mathematicians will, give a warning to other mathematicians, i.e. I'm giving a warning to you that I'm using proof by contradiction by using this phrase. So when I say by way of contradiction, I'm letting you know I'm about to do a contradiction proof, and I'm going to prove the opposite of what I'm trying to prove. So by way of contradiction, assume f of x does have two or more distinct real roots. That's exactly the opposite of what I'm trying to prove, which is good. That's how contradiction works. I assume the opposite. Okay, so now let's do some math. So I'm going to assume it has two distinct real roots. And when I say distinct, I mean they're different. So let's call them A and B. So I have a real number A and a real number B, such that their roots, remember, a root just makes the function equal to 0. A root is the same as an x-intercept. And I'm assuming here, because we need to assume they're distinct, that they're not equal. Okay, and so now I'm going to do another little mathy thing. Because A and B are not equal, one of them must be bigger than the other. And so just to make life simple, I'm going to just go ahead and say, let's call the smaller one A, and let's call the bigger one B. Okay, we can do that because if they're not equal, one has to be bigger than the other. And now let's just assign names. Call the big one B, call the little one A. So here, that's what I say here. I say, assume A is not equal to B. And then I say, and without loss of generality. So without loss of generality just means I can now make an assumption that's not going to add any extra information. So here, I'm assuming A is less than B, but that's not adding any extra information to this problem because we already know A is not equal to B. And if A is not equal to B, one of them has to be bigger and one of them has to be smaller. And let's just go ahead and call the smaller one A, okay? So that's what without loss of generality means. Okay, so now let's finally do some math and finish the problem. If you've gotten this far, then the rest of it's pretty straightforward. So now we're gonna use the mean value theorem to create a mathematical contradiction. We're going to show if we assume this function does have two distinct real roots, then things go horribly wrong. So since f of x is a polynomial, we know it's continuous on the closed interval a to b, where a and b are the roots. And I assumed a was smaller than b. And it's also differentiable. Polynomials are the nicest functions in terms of continuity and differentiability. So by the mean value theorem, there exists a number c in the interval such that f prime of c equals f of b minus f of a over b minus a. And actually, let's calculate this. And if we calculate, so you remember f of b, well, b is a root, so f of b equals 0. And f of a is also a root, so f of a equals 0. So here I have 0 minus 0 divided by b minus a. And b is not equal to a, so b minus a is not 0, so that's well defined. Yeah, so this whole thing equals 0. And so that's what I have here. F prime of c equals fb minus fa over b minus a, which equals 0. Now here comes the contradiction. Let's check and see if this is possible. Is it possible for the derivative of f to equal 0? Let's just check and see. Here, when we take the derivative, using the power rule, the derivative of 1 plus 2x plus x cubed plus 4x to the 5th is 0 plus 2 plus 3x squared plus 4 times 5x to the 4th, which becomes 20x to the 4th. Now let me plug in the c for x and take a look at the function. So here, if we look at this, 2, this is a number that's greater than 0. So this is bigger than 0. If you look at c squared, because it's squared, is greater than or equal to 0. 20c to the 4th, again, because it's c raised to an even power, this is going to be greater than or equal to 0. So if you look at 2 plus 3 squared plus 20c to the 4th, it has to always be greater than 0. The smallest it'll ever be is 2, because the derivative is 2 plus a non-negative number plus another non-negative number. So the smallest it'll ever be is 2. That is to say it can never equal 0. So I come to the conclusion that if you actually look at the function and calculate the derivative, it can't equal 0. But if I make this assumption that the function has 2 or more distinct real roots, then I can do valid math and come to this conclusion that f prime of c is equal to 0. So here something is wrong. Here we've gotten to a mathematical contradiction. One of these statements is true. They both can't be true. Either, sorry, there should be a prime right here. My bad. There should be a prime right here, which I need to fix. So either f prime of c equals 0 or f prime of c doesn't equal 0, but they can't both be true. One of them has to be true. So here, if you follow the chain of assumptions, the only place where we did something that we weren't 100% sure about was right here. This is the only place where I've made an assumption that I wasn't sure that that was true. So this must be the weak link. The reason we're getting a mathematical contradiction, and remember, mathematicians hate contradictions, so we don't like this. The reason we must have gotten a contradiction is because of this false assumption right here. This assumption that f of x has 2 or more distinct roots has gotten us in trouble. In fact, it must be that it's not possible for it to have 2 or distinct roots. And so, we've proven the original statement by contradiction. By assuming the opposite, we were able to arrive at a mathematical contradiction. So the opposite of the opposite must be true. And so here, this polynomial doesn't have 2 or more distinct real roots. This is really strange. If you're like, say what? This is because it uses logic. And so it takes time and you have to kind of read it again and read it slowly. There's a problem like this in the homework. But obviously I'm not going to put anything like this on a test because it's a little too, it's a little too weird. And it takes a little bit of time to think through. And this is really a more traditional proof, and we're not really trying to write too many proofs in this class. So if you haven't seen proof by contradiction, here is your first introduction to it. It does come up again, in Calc 2 and in other places. So certainly in your more advanced math classes, like in matrix methods, you'll see proof by contradiction a lot. Or if you're a math major, you're definitely going to see proof by contradiction a whole lot, for sure. So yeah, take a look, just get comfortable with the ideas, but don't worry about it too much for Wednesday specifically. So that ends section 3.2, and that's the cutoff for the test. So I want to start section 3.3, which is the discussion on local extrema And remember, this will be covered on exam 3, which will be in April. So we talked about absolute extrema last time. So absolute extrema are the highest and lowest values, of the range of the function. For local extrema, we defined local extrema last time. So just let me remind you, a local max at x equal to c, we have a local max at x equal to c if and only if f of c is greater than or equal to f of x for all x, and now this is the important part, in some open interval containing c, not for all x in the entire domain. So if you look here at the graph, at x equal to 1, we have a local max here at the top, at local max values f of 1. And so here's the local max value. And the most important thing here is if I take a little interval around 1 here on the x-axis, that f of 1 is larger than all those values in that interval near 1. And that's certainly true here with this little hill. Note that here, f of 1 is not the absolute max. In fact, this function doesn't have an absolute max, right? The left tail of the function blows up to infinity. And similarly, we can define the idea of a local minimum. And again, the idea of a local minimum is that it isn't the lowest point, but it's the lowest point compared to the points around it. So here you'll see in the graph at -1, we have a local minimum value at f of -1. And again, it's not the lowest point. Here, this graph does not have a lowest point. As you can see, the graph goes to -infinity. So there is no absolute min for this graph. All that's important though, is if we look at a very small interval around -1, that f of -1 be less than all those points around it. And so here we have that. So here, this would be, what we call a local minimum. Based on these definitions, I just want to emphasize that local extrema can only occur internally, inside an interval, not at the endpoints. The other definition I want to remind you of is the definition of a critical point. So Fermat's theorem leads us to conclude that if a continuous function does have a local extrema, then it's going to happen at a critical point. So I just remind you the definition of a critical point. The point x equal to c in the domain of the function, that part's important, is a critical point if either f prime of c equals 0 or if f prime of c is undefined. So a critical point is any number that makes the derivative 0 or undefined, but is still in the domain of the original function. And the reason we're interested in critical points is typically that's where our local extrema occur, and that's where potentially absolute extrema occur. So just as I mentioned for this graph, there are local extrema at plus or minus 1. There are no absolute extrema. How would we check that? So for finding absolute extrema, here we're looking at the function on the interval -infinity to infinity. So let me remind you, for absolute extrema, we check the function value. We plug in and try and find what's the y value. So we check the endpoints and the critical points. So here, critical points is no problem. We can check the critical points and find the values. But for checking the endpoints, since the endpoints are infinity and -infinity, we take a limit. And as x goes to infinity, we can show that the graph here goes to -infinity. And as x goes to -infinity, we can show the function blows up to infinity. And so that's why we're able to conclude there's no absolute extrema. So I'm going to start doing more examples of finding absolute extrema on these types of intervals where they might be, a to infinity or something like that. So this one I wanted to look at here for if it's -infinity to infinity, how do we check the endpoints, with a limit? So once we find critical points, we need to classify them. So for classifying critical points, for local extrema, we have what's called the first derivative test. Okay, so the first derivative test says that if the slope changes from positive, so here you see we have a positive slope on the left side of C. Remember, it's important that you look at the graph from left to right. So the slope changes from positive to negative, then we have a local maximum. And here in this other picture here, we still have the slope here is positive, changing to negative. And you still have, you know, a local max there. And so we use a sign chart typically to do the first derivative test. We just draw a little x-axis, put the critical point on the x-axis and check the SIGN of the derivative. Is it positive or negative, you know, around C? And then we can indicate if it's increasing or decreasing. And if it has this particular pattern, increasing, decreasing, then we have a local max at C. And similarly, for a local min, we expect the opposite slope pattern. So here, if the slope goes from negative to positive, we're expecting like a valley, you know, or a low point, and that we have a local min there. Again, with this graph, you can see the slope goes from negative to positive. And we have a min at that peak there at the bottom. The first derivative test, again, for the sign chart, just looks like this, where we're checking the SIGN of the derivative, and we're expecting to see minus plus. Of course, if it's minus minus, then it's not any type of extrema. Or if it's plus plus, then it's not any type of extrema. Only plus, minus, or minus plus will give us some type of extrema. So let me do an example here. So we're asked to find the local extrema of the function x squared times the positive square root of 5 minus x. So I need to find the critical points. And of course, critical points need to be in the domain of the original function. So you know me, I'm so obsessed with domain. I first think about the domain here. Here we need the expression under the even root, which is 5 minus x, to be greater than or equal to 0. If you move this negative x over to the other side, it becomes positive, and we get x has to be less than or equal to 5. That would be the domain. And I wrote it in interval notation as negative infinity to 5, inclusive of 5. So now let's find the critical points. So for the critical points, we need a derivative. And so here's the thought process I really hope, you know, that I want you to go through. So you're looking at this, okay, I'm doing a derivative. And what I want you to notice is that we have a product, that it's x squared times 5 minus x to the 1/2. And so I'm going to need a product rule. And for the product of the first function, since it's x squared, we're just going to use a power rule. For the derivative of the first function, we're just going to use a power rule. For the derivative of this second function, what I now, you know, want you to see is a composition. When you're taking the derivative of this second function, I want you to be aware that we have an inside function, which is 5 minus x, and then the outside function is raised to the 1/2. All right, let's do the product rule. Derivative of x squared is 2x, and so that's what we have right here, the derivative of x squared. Copy down the other function, plus copy down x squared, copy down the first function now, times the derivative of 5 minus x to the 1/2. And so here's my chain rule. Derivative of the outside, bring the 1/2 down, subtract 1 from 1/2, you know, just copy down the 5 minus x, times the derivative of the inside. The derivative of 5 minus x is 0 minus 1, or just minus 1. So at the end of the day, we end up with the derivative here. And so, you know, you should be able to get to the derivative. Now, the next step, we're done with the calculus, but the next steps are equally important. To figure out where this derivative is 0 or undefined, I have to combine this expression into a single expression. What I now am hoping that you will notice, it's very important that you notice that I've got a negative exponent here, and that this whole term, this second term, is actually a fraction. And what we can do here is to combine the fractions. What I want is I want this first term to also be over this denominator of 2 times 5 minus x to the 1/2. So I'm going to multiply top and bottom now. I'm going to multiply the top by 2 times 5 minus x to the 1/2 and the bottom here by 2 times 5 minus x to the 1/2. The 2 times the 2x becomes a 4x, and the 5x minus 5 minus x to the 1/2 times 5 minus x to the 1/2 becomes a 5 minus x to the first power right here, which, you know, I'm not going to write that first power. And then I'm subtracting the x squared from the second fraction. Now I need to do some algebra here and simplify the numerator. I need to distribute the 4x to each term. 4x times 5 is 20x. 4x times minus x is minus 4x squared. And there's a minus x squared there. Minus 4x squared minus x squared gives me a minus 5x squared. So in the numerator, I have a 20x minus 5x squared. And I want to figure out where this is 0. You don't have to factor out the common term, but I did because it makes it easier to figure out where the numerator is 0. So remember, I now need to figure out where this function, which is the derivative, we found the derivative, we found this is the simplified form. So you really need to be able to, you know, do both of these things, find the derivative using the product rule and chain rule in its raw form, and then using algebra, simplify it into this fraction. That's a really important skill here. So now a fraction will be equal to 0 wherever the numerator is 0. So we can see, if you look at the numerator will be 0 at 0 and 4. And here, a fraction will be undefined if its denominator is 0, but the numerator is not. So here, if you check, I did a limit, but you don't need to. Here, if you check, the number 5 makes the denominator 0, but not the numerator. So this makes the whole thing undefined. So this is a critical point at 5. So we have 3 critical points that I'm verifying. I'm double checking that they're in the domain. Any critical point that's not in the domain, I'm going to throw it out. But here, 0, 4, and 5 are in the original domain that we started out with up here. So we're good. So now that we've found the critical points, it's important to remember the next step is to classify the critical points. We find critical points, then we classify them. So right now we only have one method called the first derivative test. In a second here, I'll also show you the second derivative test. So I'm going to use the first derivative test. So I'm going to draw an x-axis. I'm going to put the critical points on the x-axis. I'm going to draw an x-axis. I'm going to put the critical points on the x-axis. And I'm going to check the SIGN, the sign. So here's 0, here's 4, here's 5. And remember, here, we're plugging into the derivative. Okay, that's the only thing with this. It can be a little tricky. Sometimes people say, okay, where am I plugging stuff into? For the first derivative test, we're going to plug into the derivative. And so now I'm just going to randomly pick numbers, you know, that are convenient. Like here, let me pick a number to the left of 0. I guess -1. Let me pick -1. And I want to plug that into the derivative. If you look, the denominator is always positive because it's a positive square root. So in the numerator, plug in a -1 here, you get -5. And here, plug in a -1 here, you get 4 minus -1. So I get -25 over something positive. So the derivative right here is negative. So I know the function is decreasing to the left of 0. Between 0 and 4, I guess I'm going to pick 1. It's the easiest thing to plug in. I plug in 1 to the derivative. You get 5 times 3 over 2 times the positive square root of 4. Positive times positive divided by positive. The derivative is positive between 0 and 4, so I know it's increasing. So right now, I know there's a local min at 0, because you see the pattern. It decreases, then increases. Here, finally, let me plug in like 4.5, I guess. for a number in between 4 and 5. So I plugged in 4.5 into the derivative. Every term is positive except this term. 4 minus 4.5 will be negative. So the function turns out to be negative between 4 and 5. So it's decreasing. So here I have a local max at 4. You can see it's increasing before 4 and decreasing after 4. At 5, remember the domain stops right here. The domain does not include this portion to the right of 5. 5 is actually an endpoint. And, you know, local extrema cannot happen at endpoints. So we don't even worry about 5. We end up classifying the other 2 points. At 0, there's a local min. At 4, there's a local max. And here I give the local minimum point. So when I say point, I'm giving the x and y coordinate. And the local maximum is at 4, comma, f of 4. And again, be careful to find the actual coordinate. That's f of 4, not f prime. I'm plugging into the original function to find the y value there. Okay, so be careful. And here I mentioned, since local extrema are not defined at endpoints, there's no local extrema at 5, right? So there's no local extrema at 5. But let's keep the big picture in mind. We could have an absolute extrema at 5. Absolute extrema can occur at endpoints. Local cannot, but absolute can. And while we're here, just to catalog the information we found and to review material we've learned, we also notice there's a vertical tangent at 5. Because when you look at the derivative, you can show the derivative goes to negative infinity as we approach 5 from the left. And I'll show you the graph here in a second. So I think it's really important to compare these local extrema problems with absolute extrema problems. So I want to now find the absolute extrema of this very function that we just looked at. So here, I want to find all absolute extrema of the function x squared times the positive square root of 5 minus x. Okay, so for absolute extrema, the method is totally different. That's what I want you to really keep in mind. We're going to not check the shape of the function, not check if it's increasing, decreasing. We're going to check the actual y values. Okay, we're going to check the y values at the critical points and the endpoints of the domain. Here, the domain is negative infinity to 5. Okay, so your slide may not have this negative here. I found that there was a typo. I forgot to put that minus sign in, so I fixed it. And I'll, of course, re-upload these. My apologies. So here, what I want to do is I want to check the value of the function at the critical points 0, 4, and 5, which we found on the previous slide. And I want to check the value of the function at the endpoints 5 and negative infinity. And so that's what I want to show you. At negative infinity, how do I check the endpoints? We're going to do a limit. So here, let me check the value of the function. At 0, it's 0. At 4, it's 16. At 5, it's 0. And now I've checked 0, 4, and 5. I now need to check negative infinity, the other quote unquote endpoint. I take a limit. So when you send x to infinity, since this is being squared, that's a plus infinity. And since this is a minus x, that's also a plus infinity. I have plus infinity times plus infinity. The limit is plus infinity, which means there's no absolute maximum. This is telling us that the graph, when you go to the left, the graph goes up forever. So there's no absolute maximum. So we have an absolute min. If you look at all these numbers, 0 is the smallest number. We have an absolute min value of 0, which occurs in 2 places at 0 and 5. And we have no absolute max, since one side of the function is blowing up to infinity. And you can check the graph looks like this. And this graph is basically from just following the increasing, decreasing behavior, plotting the extrema. So this point here is an absolute extrema, but not a local extrema. This point here is an absolute min and a local min. This point right here is a local max. And remember, there's no absolute max because the function is going to infinity. So let me talk about concavity. Concavity has to do with kind of the direction in which a curve might curve. So if you look at this first picture here, we have the definition of what's called concave up. And you can see the curve is pointing upwards. So what happens in concave up is, so here you can see, look, I have the slope here is negative, then the slope's 0, then the slope's positive. So the slope goes from small to large. The slope is increasing. So here, when the second derivative is positive, we know the slope is increasing, then we'll have a concave up curve, and the curve will, in this case, lie above its tangent lines, just like this picture here. You have your concave up. And similarly, if the curve lies below its tangent lines, like here you see you've got positive slope, 0 slope, negative slope. So here the slope is decreasing, which means the second derivative is decreasing. And when the second derivative is less than 0, we say the function is concave down. And you can see the function is cupped and pointing downwards. And in this case, the graph lies below its tangent lines. And, these are just features of how a graph might behave if its second derivative is positive or if its second derivative is negative. We get this concavity behavior. And along with concavity is the idea of an inflection point. So a point in the domain of the function, maybe I should have, emphasized that. I said on the graph of f of x, so that means in the domain of the function, is an inflection point if the concavity changes from positive to negative or negative to positive. And that the point, it's an x and y coordinates called a point of inflection. So here we have two examples. So here we have this function goes from concave down to concave up, and the point of inflection would be at the origin. And here you can see at the origin, we also have a horizontal tangent. So that's one way, the inflection point can occur. The other picture you should think about is if you flip this over. Flip this picture over, and we have a graph like this. And so again, this would be an inflection point at the origin, but now concave up to concave down with a horizontal tangent at the inflection point. Compared to this other one here. Here, this goes from concave down to concave up, but there's a vertical tangent right here. Okay, and again, it's important to look at the same picture, but flipped about the x-axis, right? So that we have something that looks like this. Oh my God, I'm trying. That's supposed to go through the origin and be a vertical, but yeah. So this would be concave down to concave up, where the point of inflection is occurring at a vertical tangent. Okay, so these are two good prototypical graphs just to keep in your mind for curve shapes and concavity. So how do we find inflection points? Well, inflection points, it's when they occur, can occur where the second derivative is 0 or undefined. So what do I mean by can? We still need to verify. How? We have to actually check the concavity. We have to check and see, does the second derivative go from negative to positive or positive to negative? It's possible to have the second derivative be equal to 0, but not have a point of inflection. So like a curve like this that's concave up and then concave up again is not going to have, a point of inflection. Or a curve like this where it comes up, but then it goes back down. That's not going to have a point of inflection. That's going to be concave up, So if we use the first derivative information and combine it with the second derivative information, we get what's known as the shape information of the curve. And the easiest way to show that to you is I did a little diagram. This is typically what I show to my students. It's not in the book. So here, if you have a curve that's concave up and increasing, then the only possible shape has to look like this. And remember, it's imperative that you look at these curves from left to right. If you have a curve that's concave up but decreasing, then the only possible shape is it has to look like this. There's no other way to be concave up and decreasing if you look at left to right. Similarly, you know, if our curve is concave down and decreasing, this is the only possible orientation. And if it's concave down and increasing, this is the only orientation. You know, sometimes when I'm doing graphing problems, I'll just draw this little shape in the corner of the page and no one knows what I'm doing, but I know what I'm doing. Like, this is my little shape guide. Concave up increasing, concave up decreasing, concave down decreasing, concave down increasing. So once I can figure out where's the function increasing and what's the concavity there, I can figure out the shape. And then once you plot some points, you've got the whole curve. You know, and we'll work on that in section 3.4 in a big way. The other thing I want to just emphasize is that we classify local extrema using the shape, okay? And we classify absolute extrema using the value of the function. So I have a little example here to show you what the heck I'm talking about. So in this example, if you look, we have a local min right here. We have a local max right here in the third quadrant. And now if you look, the y value of the local min value is actually larger than the local max value. So that's why we're using, you know, shapes here. It's this shape here that makes this a min. It's this shape here and this little peak, you know, that's what makes it a min, not the actual value. That's why for local extrema, this is really important. We look at the shape. Is it increasing, decreasing, or decreasing, increasing? We don't plug the points in. But for absolute extrema, we plug the points in. For absolute extrema, we do want to know what's the largest y value, what's the smallest y value. So we're looking at the y values. For local extrema, we're trying to identify little bunny hills and little valleys. So we're doing that with shape. Okay, so that part's really important. There's a second derivative test for local extrema. So this is instead of the first derivative test, and it uses the concavity. And it's for horizontal tangents only, okay? Because otherwise the second derivative isn't defined. So if we have f prime c equals 0, and the second derivative is negative, then the function will be concave down. So we'll end up with a local max when it's concave down. And for the opposite case, if f prime c equals 0 and the second derivative is positive, if it's positive, that means the graph is concave up. If the graph is concave up, then we have a local min here at the bottom. So, you know, you can use first derivative test or second derivative test to classify the critical point. It just depends on what's easy. Sometimes it's very easy to find the second derivative, so I go ahead and use the second derivative test. Sometimes it's easier just to plug in numbers to the first derivative because the second derivative is very complicated, you know. So in that case, just use the first derivative test. But here you do have two options. And, you know, of course, it's in your best interest to know how they both work. One will be easier than the other to use in certain situations. So I believe I was gonna start doing an example here, but since we only have 1 minute, I'm not gonna get into the example. I'll just finish this up on Monday and it'll fit with our curve sketching, which is the next thing we're gonna start. So I'm gonna stop right here.